Hello everyone, thanks for coming. Today we are going to do a review of our week 7's lecture in linear algebra. So in this week, we introduce orthogonality, orthogonal subspaces, and projections. So first of all, we define the orthogonal complement for a subspace. The orthogonal complement is another subspace that contains all vectors in the whole space that are orthogonal to any vector in the given subspace V. So it's called V orthogonal. For a matrix A with rank R, the null space is the orthogonal complement of the row space, while the left null space is the orthogonal complement of the column space. The dimension of the subspace V plus the dimension of its orthogonal complement equals to the dimension of the whole space. Therefore, you can verify that the dimension of the row space plus the dimension of the null space equals to n, while the dimension of the column space plus the dimension of the left null space equals to m. The equation Ax equals to b is solvable only when for each y in the left null space, b is orthogonal to that. So this is another viewpoint to justify whether Ax equals to b is solvable. Under the orthogonal viewpoint, we can also treat the linear system Ax equals to b in a different way. Every vector x in Rn can be decomposed into x equals to xr plus xn, while xr lies in the row space of the matrix A, while xn lies in the null space. Therefore, Axn equals to 0, while Axr belongs to the column space of A. Therefore, the matrix A actually maps its row space onto the column space. So, from the row space to the column space, it is invertible. If A inverse does not exist, then the pseudo inverse acts as an inverse on the row space. Basically, the pseudo inverse converts a vector in the column space back to the row space. Orthogonal complements basically splits Rn into perpendicular components. As you can see, we decompose x into xr plus xn, and xr belongs to the column space, while xn belongs to the null space. So orthogonal complements basically enables projections onto subspaces, as we just did. With orthogonal complement, with projection, we can formally define cosines and projections. So for any vectors, the cosine of the angles between two vectors is defined as the inner product divided by the normal A times the normal B. The cosine of the angle ranges from -1 to 1, therefore we have the Cauchy-Schwarz inequality. The absolute value of the inner product of A and B is smaller than or equal to the normal A times the normal B. Equality holds only when one vector is a multiple of the other. That means they lie in the same direction or lie in opposite directions. So this is how linear algebra connects with geometry. Finally, we can also define projection using inner product and orthogonality conditions. The projection of B onto the line spanned by A is defined as P, and the formula is given by A transpose B divided by A transpose A times A. So the multiplier A transpose B divided by A transpose A is scalar. If we change the sequence, we can rewrite P as A times A transpose times B divided by A transpose A. So this matrix A times A transpose divided by A transpose A is called the projection matrix. It is symmetric, and P squared equals to P. its rank is 1 because it has a standard form of a rank 1 matrix. So in this way, we have another viewpoint to define transpose. The transpose, A transpose of a matrix A is defined as a new matrix such that the inner product of Ax and y equals to the inner product of x and A transpose y for any x and y. So this could lead to the important identity, the transpose of AB equals to B transpose A transpose. Thanks for listening.